Okay, so thank you so much for organizing this wonderful, inspiring workshop in such a nice place and for inviting me. It's really nice to be here. You know, it was miserable, rainy, and cloudy in London, so. So, all right, so the title of my talk comes from a recent paper, How Can Large Language Models Learn from Humans? And I quickly went and changed it to how can they become more naturalistic as a result of this workshop. And this is research supported by, actually, it's Royal Academy of Engineering and UCL for University College London. And it's with a group of lovely people. This is Daphne Wang, my former PhD student, Wingy Chow and Richard Breheny. They are psycholinguists from UCL's Linguistics Division. And that's Miloš Stanojević, who is a research scientist at DeepMind. And we work in this lab called Principles of Natural Language, Logic and Statistics, which is funded by the Royal Academy of Engineering researcher. All right, so just to recap on large language models, everybody knows what they are, just very quickly to put us in context. When I was doing my undergraduates and, when we took computational linguistics modules, we worked with LLMs, so language models. So these were basically Markov chains trained on statistics of words or characters over a corpus. And this was ages ago, and they've come really a long way, leading to large language models where the statistics are learned using much more sophisticated learning algorithms, deep neural networks with attention mechanisms and transformer technology. And in those old days, you would never dream of asking your language engine such a question. I feel really tired. What should I do? You would definitely not give any answer like that. Nowadays, even if you go, one generation before things like the GPT model, you can look at BERT. This was the first, contextualized transformer algorithm. So you could mask anywhere in the sentence, in the middle, at the end, at the beginning. And if you say, when really tired, ... it would tell you all these things. It would fill it up, it would give you a list of things you can do. It would rank them. You could go, read the previous hidden layer, extract probabilities. But you would get this. But nowadays, if I ask ChatGPT, you'll get something really nice and organized that goes the extra mile, like this. And my mom or my grandma could not do a better job, like telling me what to do when I'm really tired. Definitely giving a talk is not one of them. All right, so obviously a lot of people, as you've seen here so far, they criticize large language models. There's many things they cannot do. They have shortcomings and weaknesses. And lots of these have been identified, and you can sort of add them, and they become better as a result. What we have been thinking on is this thing up here in red, that those language models, they learn by prediction. And there's a problem if you want to do more humane calculations, that these predictions are only at the lexical or word level, and this is not what humans do. In fact, it's quite interesting. Psycholinguistic research, it shows that people learn a lot based on prediction. The fact that I can talk so fast and you can understand me and you can read a piece of text very quickly is because we do really learn by prediction, by forethinking. However, research also overwhelmingly shows that this prediction is not just lexical, it's not at the word level, but it's a lot of prediction at many different levels is at work. For example, we do think about the grammatical rules of what might come, so that's syntactic prediction. You do think about the meaning of what might come next, semantic prediction. You do really also think about, the larger context, the consequences of what you're reading about, the consequences that the common knowledge or the common sense, external world knowledge that it might give to your head. This is called the pragmatics. These are like at the word level. You can also go at the character level. And there is also evidence that people do prediction at the phonological and morphological level even. And this has been shown using many experiments, and we're going to use a test case which is called garden path sentences. And I'll try to explain. So here's an example of a garden path sentence. As the woman edited the magazine, entertained the guests. So garden path sentences, they are known for having endemic temporal ambiguities. So here, when you're reading this sentence, you will get a little bit confused around here. But the sentence as a whole is not ambiguous. So this ambiguity goes away by the time you get to the end of the sentence. But as a result of this ambiguity, and for you, in order to understand the meaning of this sentence, you will stall in this critical region, you slow down, you look back, you reread it. And this will increase your reading time, as opposed to a disambiguated version when, for example, there was a comma here. That would have a much shorter reading time than the garden path version, when you sort of either drop the comma or do some syntactic manipulation that makes it disambiguated, even endemically. So I bet you all know why that is, but just to be a bit pedantic. So this is how a human is supposed to read. You see as the woman edited. You think, right, what does this mean? Well, I can for sure say that this is a subject. There's a subject-verb at play here, the woman unedited. So based on that, you predict what might come next. You saw a subject and verb. You think, what can come next? Any suggestions? Object, well done. Anything else? What? Comma, well, if you, yeah, maybe. Not all the time, but similar. So you can have an adverb, you can have a preposition, you can have a sentence complement, a relative clause, and so on and so forth. Now, what comes next is actually a noun, the magazine, and you say here, Lea bingo. I've got my subject-verb-object structure. Now, what am I waiting for? Maybe another sentence, comma, another sentence, an adverb, again, prepositional phrase, so on and so forth. But what comes surprises you, and that's another verb. And here, having assumed that magazine is the object of the first verb, you are sort of startled. It cannot be that, because you've got seen a verb here, and the verb has to be preceded by a subject, and this guy isn't that. So this is where this cognitive dissonance happens. Subject-verb-object clauses are not normally followed by a verb. So you have to sort of go back, rethink it, read it again, or go forward. By the time you get to the end of the sentence, you've seen the guess. You've gone back and forth a few times. Some garden path sentences need 8 times reading to understand. Then now you understand that this magazine is actually not the object of the first verb, but the subject of the second verb, right? This is an SVO structure. And then you are happy, and I guess everybody realizes why this is called a garden path sentence. The first reading, one of the possible readings, which is not the final correct one, will lead you across a garden path, which is not the correct one. Then you have to backtrack and then choose a different set of interpretations. It's actually quite interesting. We are not quite sure how far you have to backtrack, to go to the word before, to the sentence, to the beginning of the sentence, to go first forward and then back. These are not worked out, but all we know is that there's a certain amount of back and forth going on. Okay, right. So as a result of this back and forth, obviously human reading time increases. What I want to argue here is that doesn't happen in large language models. So you should ask, why does it not happen? And what do we even mean by saying that these language models, they don't read like humans? Can we even talk about the notion of time, reading time in large language models? And luckily, this has all been solved by some other people. So I'll just reference their work. So historically, these garden path sentences, they were introduced by Thomas Beaver in Arizona University. He was a computational linguist, and interestingly, he put this forward to show that the primordial structure that humans have to understand language is not what Chomsky thinks, which is syntactic structures. It's what he calls semantic relations. That's why he put them forward. He argued that people fall into these tricks because certain structures are semantically primordial in humans, for example, that of a subject-verb-object. And he gave some reasons why does he think that. This may be because subject-verb-objects are easy to learn. The mother tells a lot of sentences in that form to the child, so on and so forth. But he came up with a lot of different types of garden path sentences. But that was, ages ago. And it was also done in, linguistics department, where probably people didn't care about statistics. And it wasn't until, 2000s and the work of John Hale, Johns Hopkins University, that he said, hang on a minute. In fact, I can prove Beaver's theorem by using an information theoretic measure called Surprisal. Do people know what this is? I have no. Maybe I can write it down. So the Surprisal of Wn given W1 to Wn minus 1 is minus log of just the conditional probability to W1 W2 minus 1. So he basically argued Surprisal and human reading times move in the same direction. The more surprised you are, the more time you read, you need to understand what you're reading. Very, very interestingly, though, he didn't work with semantic structures like Beaver was arguing. He worked with syntactic relations coming out of a statistical parser. It's the early parser. He had a bunch of examples. I want to say 5, but probably there was 3. He looked into this early parser. He read off the statistics. And he showed that Surprisal and reading time, move in the same direction. As the parser gives statistics that lead to Surprisal that is higher in garden path sentences versus the disambiguated controls. A bunch of very influential papers came out, but he hadn't worked with this theory in large scale. The first set of large-scale results were as a result of the work of Levy, and then Smith and Levy, a lot of other people. They looked at large corpora of data, Wikipedia, Google News, and they really verified it. They got people to read those sentences. Hale didn't; he just guessed. They got people to read. They recorded their times, and then they calculated Surprisal, and overwhelmingly they found correlation. They even conjectured, a coefficient. Surprisal times a certain number will give you reading time. However, the sentences they considered, they were not garden paths anymore. They were all naturalistic examples. They forgot about garden paths, was at this point forgotten. They just worked with naturalistic data. So I want to say this has also been tested on many different languages. A recent paper shows also correlation for 5 different language families, many different languages in these families. And then they appeared the work of another bunch of people led by Tal Linsen, New York State University. He's a psycholinguist who also cares about statistics. And they started working with these old psycholinguistic datasets that were put forward as a result of the work of Beaver. And they, paper after paper, and this is just a few of them I'm citing here, there's quite a few more around, they showed that in fact Surprisal does not correlate well in garden path sentences. In those data sets designed by psycholinguistics, when they use eye gazing, they calculated human times. If you do your large scale analysis, if you calculate Surprisal, you are not going to correlate with human reading times. They use quite a few, very sophisticated methods. They combine syntax with semantics, with parsing probabilities, put weights in, and did their best. And they felt even if, in some points, Surprisal might correlate to some extent, to garden packs in general, garden path sentences come in different voices, different grammatical structures lead to very different reading times in humans. You've got easy versus harder garden path sentences. And Surprisal definitely cannot distinguish between the two. I'll show some results at the end, and you'll see how bad the situation is. And so the work of this paper, me and my colleagues, we sort of thought of a solution here. So obviously, you need a mathematical framework that can combine statistics with structure. And this is a very simple framework. So it's called the theory of event presheafs, but actually we work with very, very simple types of them, which are not as complicated as the most general version. I bet a lot of people in the audience know about presheafs much more than me, so I apologize, this is too simple. But what is interesting is that whenever you have a presheaf, you talk about a base, which holds the structure for you, and that is, for our case, a preorder suffices. So you have got the set X with an ordering on it. If you want to model real data, you better also, these are called event presheafs because you want to ground them on data. And you also talk about events. And these events are maps S from elements of the preorder to a set of outcomes O. So you have these events. You run the events. This can be observations, measurements. It can be the comprehension, reading, understanding. And as a result of that, you gather some data. And the data is you collect in the image of this presheaf. So a presheaf is a map. It is applied to the partial order. It takes an element therein, U in X, and it returns a set of data on this element. It can be anything. It comes from these events you're interested in modeling. For us, it's comprehension. But the presheaf has another interesting property, and not only it acts on the elements of the partial order, it also preserves the partial order. And by that, we mean that if V is, or preorder, it's less than U, V is included in U, think of them as set and set inclusion, the presheaf map preserves this, i.e., the data on U has to be restricted to the data on V. So this restricts P of U to P of V, the data on U to data of V. That's how it preserves the partial order in the opposite direction. So that's why if you do category theory, you think about this function from a category C up. For us, this is this thing category, preorder category, to the category set, category of sets and functions. All right, so here's like a visualization of this restriction property. So you've got U, it includes V, you've got the data on U and the data on V, and the data in U about V shouldn't come from just anywhere. It should be the projection of the data of V in U. So it's a very, very simple consistency or compatibility criteria. This is, I think, what makes presheafs interesting, the restriction feature of them. All right. In this simple partial order case, you won't see anything fancy like this, but people who work with sheafs and presheafs, they would like to see this definition, that of gluing. So if U and V, V is not included in U, but they have an intersection, you also want that the data of the intersection to be consistent with the intersection of the data. That's what the gluing says. So you've got intersection U with V, you've got the data of the intersection, but you've also got the data in U about the intersection and the data in V about the intersection, and you want this to match. Okay, so far so good. Everybody happy? Yeah. So what happens next is when you have, you've got data, you've got your events, and you want to have probabilities. The goal here was to combine statistics and structure. Here we have talked about structure, but where are the probabilities? And then it's really easy now, because then you can just compose your presheaf map with a distribution map, which just, so call it D, your distribution map. So D of P is also a presheaf to elements of U. of your pre-order, it assigns distributions, and it also preserves the ordering, the initial ordering, but just taking the marginals of the distributions when you go from when you project V to U. And these are called probabilistic event presheafs. It's just, I think it's a very simple structure. Maybe I'm just being pedantic, going over it a lot. So here, your partial order, like Titan I was showing us, it's just like prefix order. You've got A, these are the most obvious partial order in nature. You've got A, then you build on it, you've got AB, and then you build it, you've got ABC. You're interested in observing this in different lights. So you're going to measure them and think like A is green and AB is green and blue, and so on and so forth. So these are your measurements, information about these strings. Maybe there are some codes. Based on these observations that you do, you have some data, and you repeat your event, and you have some probabilities, which for some reason I haven't added. Sorry, forgot. You've got your probabilities. I thought I have it, but it's gone. So this is your P map, the data map. Then you just add your D map, and you have your probabilities, right? You repeat the event. Obviously, you can calculate probability. For human sentence processing, this is also really easy. We've got a vocabulary. So you want to take this to be the vocabulary of your language. But because I'm modeling this garden path sentences and I've got a data set, I'll just take the vocabulary to be the vocabulary of this garden path sentences. Everything is quite finite. And my partial order is the set of phrases over this vocabulary. For example, this like as the woman read, as the woman read the magazine. These are all elements of my partial order. Why is it partial order? Sorry, a pre-order, but it doesn't matter so much because of the prefix ordering that I have here, right? It's nothing sophisticated. It's just the linear order of time as I read it, right? If I go from left to right. If this was Farsi, this was from right to left, but it's from left to right because English. So what's the data over this? For what I want to model, these are completions over these subphrases or the predictions that you have for each subphrase. That's the data of the presheaf, the set of completions of each of these. And what's the event? The event of understanding, comprehending each subphrase. How? By assigning an interpretation to it. And here now things become a bit fuzzy. What does it mean to assign interpretation? What are interpretations? And if we want to be simplistic, we just say, yeah, these are just like, if you comprehend the subphrase, if you know its syntactic structure, its semantic structure, its pragmatic, consequences, all of them together. But you sort of bunch this up together. So we have so far just worked with syntactic structures, as you saw. So you see, as the woman read magazine, just as I had in the beginning, you have got your subject-verb. You have these completions you think about. So as the woman might read, she felt nostalgic, she became tearful, then you carry on. Because you've now one extra word, then you change your completions. As the woman read the magazine, she sighed. Then you see your next subphrase, the next word comes in, entertain. Then it becomes a little bit difficult for you because you sort of struggle to assign a completion because you've seen a verb. You get a bit confused, right? And that's where stalling happens. And the confusion, right. So it seems, sorry, I'm going too fast. Let me see. Okay, so how much time do I have? Half an hour, okay. Maybe I can go slower. So then you can see here, not only people, they sort of come with completions of these subphrases, they also rank them. So there is a notion of probability there. And it's not just like a simple ranking, they have weights. So according to your background, according to your environment, and the things you've seen and learned, you're going to rank these sentences with different degrees of plausibility, which give rise to probabilities that I'm trying to denote here. So completionist probabilities, then a dissonance happens basically when either what comes next is not what you had seen before, what you had thought about before at all. It was not in the completion of the previous subphrase. It was definitely not there. So this gluing property fails, and that's where the dissonance happens. Or it is there, but it's really with a very, very low probability. You are not at all expecting to see it. Suddenly it happens, and then that's again causing dissonance for you. So how do we calculate? Yes.
Can we use this framework to understand how children acquire verbs? For example, a lot of Pinker's work talks about how children learn to say pour water into the glass, but it's wrong to say pour the glass with water, for instance. So the syntax of a verb is that it operates on these different arguments, but the semantics is based on experience, and some ways of using the verbs are correct and some are just very unnatural.
So your question is, does this also apply to semantic interpretation?
Can we use this to understand how we humans learn verbs and use verbs?
I don't think there's a theory of learning here. So you can argue the completions come from how you learned language. Based on that, you sort of you come up with completions and then rank them based on how you learn language, and that's why something like an SVO will rank much higher than something than SVS, subject, verb, subject. Because, for example, when you learn language, you haven't seen a lot of this. Actually, maybe I get your point. So maybe it's, this also goes, at the semantic level. Different verbs, they treat the agents and the patients differently. And that, so it's definitely not just syntactic structure. You do think about what is the thematic role of the verb and what kind of object it's expecting. And those come into the picture too. So I have not covered it, but definitely there's room to do it. Yeah. Right. So, but I think the thing is that you've got your probability distribution of the larger phrase. Here, probability distributions over the smaller phrase. Here, then you can calculate a divergence, a distance between these probability distributions by looking at the probability of the larger one, restricting it to the probability of the smaller one, and then calculating how far away it was from the probability that you originally guessed here. The notion of restrictions in sheaves allows us to even think about it in this way, and that's what was the game breaker here. So we call this divergence incompatibility fraction. So this is the degree of cognitive dissonance caused by doing this correction, which is taking the divergence of the probabilities of interpretations of the larger subphrase, M1, M2, restricted to M1, and then you compare it to the probability dM1 over all possible extra syntactic roles, in this case, semantic structures, if you want, pragmatic concerns, that the new addition has. So you see the sheaf restriction comes into the picture here. To calculate a divergence between two probability distributions is nothing new. We have a lot of measures to play with. So you've got KL divergence. It's lots of times undefined because this dividend is very small. In fact, in our case, this was really small in many cases. So we had to work with the symmetric version of this, which is called Jason-Shannon. Basically, you take average of one divided by the other, and then the other way around. And then this one, which we came across just accidentally, this is called the Earth movers distance. You take the minimum of the distance differences. and then you add them, and 1 minus it will give you, the dissonance rather than the effort. And that's the formula for Surprisal, as you've seen here. As you can see, they're very different. Here you've got your restriction, at place. Here you don't have any such thing. You just look at Wn given W1 to Wn minus 1. Just look at basically conditional probability. And the restrictions going back and going forth does not come into the picture at all. The structure of these phrases don't come into the picture at all. So this was when we ran some experiments. First of all, how did we collect the data? So we used completions from the GPT-2 model. And then we passed these completions to Spacey. This is a transformer-based dependency parser. So we got the grammatical structures of the completions. Then we grouped completions that had the same grammatical structure, and using the probabilities that you can read of the GPT model, calculated probabilities for groups of completions that had the same structure. Easy data collection method. And then we experimented with 4 different psycholinguistic datasets. So 2 from a paper by Pickering and Traxler in 1998, and 2 from a paper of Stewart and Pickering, and that's from 1999. They were developed for different reasons. The one of Pickering and Traxler was actually not only it focused on syntactic structures of Garden path sentences, they also tested for plausibility, semantic consens. This one was just for syntax, and they didn't care about plausibility. They have very simple, structures. Each of them has 24 sentences, which are easy garden paths, and another 24, which are hard garden paths. So here you see an example of the easy garden path. The dog catcher worried the terrier, which fell, wouldn't fit into the box. And this one is after the judge decided the verdict of the trial caught the old man's attention. So each of them have 24 easy, 24 hard, and they also have the disambiguated controls. So for each garden path sentence, you also have a version of it that resolves the endemic ambiguity, and it's basically easy to read. Here are some nice results. So for each of these sets of data sets, we trained a regression model and calculated the degree of correlation between human reading times and our different measures. So here you see for this incompatibility fraction, the Earth mover's distance, you get the highest row, nearly 0.6. Correlates really well with human reading times, and it's got also a very strong p-value, which is a very good sign. It doesn't work so well for KL, but it's not actually that bad. For Jason Shannon, you get the second best, 56, with also a very low p-value. But contrast this to Surprisal, which, okay, that's an okay correlation. It's not negative, but it's actually not trustable because it's got a very, very high p-value here. So what came out of it is that, so when you have these correlations, then you sort of design a prediction task. What do you want to predict? You want to predict what's called the garden path effect, the difference between reading times in garden path sentences versus the disambiguated versions. And obviously, this has to be quite high, right? If you look at human first pass, 39.5 milliseconds difference between garden path and non-garden path. And if you look at our models, this IF min comes really close, 39.47, really close, really bingo. The other 2 models weren't that bad. Jason Shannon follows suit very closely. KL is not so good, but Surprisal is really not okay at all. 0.35 in comparison to 39.5. Yes.
Did you say the human first pass is millisecond? Is it time?
Yeah,
Yeah.
these are all times, milliseconds, yeah.
And what are the
totals?
No, the numbers associated with the methods.
These ones,
Yeah, they also milliseconds.
they're all milliseconds, yeah. So you use the correlation to come up with the coefficient. And then from these, then you predict the reading time. So these come from these, regression equations. And yet these are all, so this is just Spearman's correlation, but these are proper reading times. So this for humans, nearly 40 milliseconds, and these are for our models. Yeah, do you see the difference between, IF-min and Surprisal is quite high. They're not doing really well at all. But moreover, also, if you look into the data and you look at this classification between the hard Gaussian path and the easy Gaussian path, there's also quite a contrast for humans, 46 milliseconds versus 32. And in our model, you see here, the GCS worked better, 52 versus 27. This obviously, the easy ones are a bit underestimated by the model, and the hard ones are overestimated. But it's fine, because if you look at Surprisal, you'll see for the easy ones, it went negative. And for the hard ones, it's really not existence at all. It's really small. And that's why Linzen, they discovered Surprisal doesn't work well. But now we've got something that works quite well. A very similar observation, about the other data set. Then again, because KL didn't work as well as JS, so we just didn't use it. So again, the raw values, are quite high for both of our measures versus Surprisal. This doesn't, on its own, doesn't matter so much, but the p-value is so high, you don't want to trust this. So you don't see what happened there. These are just the times again, comparing to humans. This one, the IF-min is very noble here, comes quite close. On the estimates, the hard ones, there's 400 milliseconds, there's only 137. But Surprisal, again, acts very erratically. This one is really low, and this one goes negative now. All right, so I'm happy to round up. So this paper, with some of these results published, this got the Best Paper Award of, did I say that at the beginning? I completely forgot. So this is our newest paper. It was presented at Cognitive Models of Computational Linguistics, and we got an award for it. A predecessor of it, different data sets, different data collection methods. This appeared in Transactions of Rural Society. And then we've been on this for quite a while now. Yet a predecessor appeared in this Martha Lewis's Semantic Spaces workshop, and it's in the proceedings there. And again, this previous version came from an extended abstract in this workshop, Quantum Contextuality in Quantum Mechanics and Beyond, and it got the Best Paper Award there as well. Maybe I can say something about these quantum connections at the end. But I can wrap up now. So in conclusion, combining psycholinguistic theories with large language models make things better. Yeah, do you agree? It's definitely not useful to throw them all away and just work with these statistics. So we showed just one case of this. There's lots remaining to do. So here we've really presented a very contrived model, do you agree? For interpretation, human comprehension, which is by far something really big. We just looked at syntactic structure. We are thinking about adding semantics to it, using abstract meaning representation. So exactly like Spacey, you've got software that gives you the semantic structures of the sentences. You've got your Darling first order logic that that also provides semantics for these sentences. You can work with easily encodable, I would say here. People like Pado and Keller, they work with sort of clustering co-occurrence data on the different themes of verbs, as you were mentioning. That also gives you a notion of semantics and works quite well in the one of the data sets that was probed for semantics. So we can easily integrate all of that in our model. For pragmatics, things become a bit more difficult, although there exist data sets that test for pragmatics. They give you larger context for these sentences. And there are some theories, but the theories here are not as formal. Maybe it will take a bit longer, or maybe it's not possible to sort of bring pragmatic concerns into the account here. Maybe we have to use knowledge graphs or probabilistic knowledge graphs or something like that. But I feel like, all of this, they are possible. So we can improve our theory of interpretation. What I would quite like to do, which my co-authors tried to stop me, and that is working with multimodalities here. So what's the best way that I can tell I've understood a sentence by imagining a picture of it, some audio, maybe a taste or a sense of touch. And I think all of this can also be done. You easily these days, you've got your image, you can create audio related to it. Maybe smell and taste are not there yet, but you can also include those as the real interpretation of a Gothenburg sentence. That's quite interesting. A very old study by Steedman has shown that if you bring in multimodalities into the picture, so they showed images to people when they were reading these garden path sentences, and the reading times increased enormously. It's not surprising. So we wonder if we can get these results here. The other thing is, really, I don't see a large difference between Surprisal and the incompatibility fraction. It's just the Surprisal is not applied, is not used in the right way. I'm going to say some dumb things about this. So if you look at this formula, that's the winner. So you calculate your probability distribution of the larger phrase restricted to the smaller phrase, and then you calculate the difference. This is not what Surprisal is doing. Poor Surprisal. Who said it has to do this ever? And in fact, it's not impossible that instead of this Wn, I can look at W, n minus 1, and instead of this sequence, I can just restrict it to its previous version, and then when I'm calculating this divergences at each stage, I'll just calculate Surprisal there instead of calculating KL or the earth movers. I can calculate Surprisal, but over these phrases and their restricted versions. We haven't done that yet, but I think this has a good chance. In fact, Surprisal worked so well with naturalistic data. There was a suggestion by one of the reviewers. Maybe you want to look at the overlap between Surprisal and IF and work with combinations of the two, where one of them works well with naturalistic data and the other one with challenging data. So that's something else we want to pursue. The other thing is that, we also, this is statistical natural language processing, but our data sets are quite small. 48 is nothing when you come to NLP tasks these days. And in fact, Tal Linsen and students, they did think about this problem. Now we've got a large scale, thousands of elements, garden-based sentences. So this is called the SAP dataset. The psycholinguistic datasets are small for a reason, to collect human reading times. You really have to hire these humans, put them in these dark rooms, in front of an eye tracking device, pay them a lot. They have to sit in front of the screen, read. It takes a long time and it's expensive. And that's why those data sets are rather small. This large data set of garden path sentences try to overcome this by working with self-paced reading rather than eye tracking. This is when you read the sentences in exactly the same way as I was introducing them. You see the first word, then you see the second word, then you see the third word. As you want to go forward, if you think you've understood the previous phrase, you push the space bar and you see the next phrase. And you carry on, but with the caveat that the previous words that you've just read disappear. So this is very hard. In fact, I try to do some of these sentences, and it's really confusing. Like you forget what was there before, and then stall for a long time and just use memory and some guesswork. So as a result, the human reading times are quite large. So there's an idea around that we might want to apply for a grant and collect fMRI or EEG. There are modern versions to collect, look at the brain where the spikes are, and that's how you sort of model human behavior. We might want to do that. But something else that is, less incremental and more interesting is modeling reanalysis. So here we just looked at the flow of time, You look at your first word, then you sort of go forward. It's all forward looking. But when there is a problem, you want to go back and then go forward again. And this is not part of my pre-order at all. This is not the prefix ordering that we considered. So it would be really lovely if we can look at causal orders or some kind of Bayesian models. Human theories do not exist here because it's very difficult to see if humans went back and how far did they go back using eye tracking. So here I think we can actually provide some insights for human behavior. In fact, with Daphne, we've got a paper where we use causal orders. We just show the existence of a backward order for garden path sentences. And that is more probable than the forward orderings that you have for the challenging cases. So I think this is really lovely. That's promising to work on. Finally, about the connections to quantum mechanics. So I came to use sheaves because some quantum people across my corridor, they were using sheaves to talk about contextuality phenomena in quantum mechanics. So this is when you run experiments and you collect probabilistic data about the results of these experiments, electrons being spin up or spin down. And this probabilistic information does not match the classical probability theory that you have. So you have to come up with a new theory. This was pinned down by Einstein ages ago. And the theory of contextuality is one theory that explains this, the strange statistics that quantum systems show. But what's happening here is that you really got a sheaf structure. You've got your probabilities. You've got your structure, which is the rules of your quantum mechanics, and you've got contextuality, which tells you there are local ambiguities that don't give rise to the glue that you have on the top. Thank you. So as I was, walking in the corridor, I could hear the quantum people talking about local ambiguities and lack of a total gluing, and this sort of was a signal that probability shifts can also be used to model garden path sentences, and that's what pushed this forward. But at the same time, it's very tempting because quantum contextuality is a very rare phenomenon. It only happens in very small percentage of even quantum data. What do I want to say here? It's tempting. If you're after a challenge, you're like, oh gosh, can I find quantum contextual examples in natural language data? And so I've put, a bunch of PhD students to sort of be charmed by me, and we try to do these things together. Sorry. And it turned out whenever you look, you will find your quantum contextual examples. They're always there. It doesn't happen in this pre-order because on the base, you don't have a circle. So if you want to find quantum contextuality, this shouldn't be a pre-order. You need a cycle. But it's actually quite easy to think of situations where you have cycles, and then you collect your statistics using the GPT model just by asking Amazon Talk participants. Just browsing the web, and you will always find these quantum mechanic cases. So contextuality in quantum mechanics, after all, is not such a weird thing. We've now got a paper in the quantum technology and machine learning, and we had a paper last year. And one of my students is also trying to find out if there is a connection between the degree of contextuality, which is a fraction very similar to our IF, and the IF that we get here in natural language. And that's it. Thank you.